So let's talk about character codes. Character codes are a mapping of characters, usually letters, but other things, to numbers and back. And that mapping allows computers to process language, which is a really important thing. That's part of what makes computers able to do so much for us. So we're going to look at the history of character codes, starting with communications codes and data processing codes. Both of these codes are much older than computers. Eventually, computers take ideas from both of those systems and produce the thing that we use today. So we're going to start with the Morse code. The Morse code was designed by Samuel Morse, an American portrait painter. He also had a hobby playing with electricity. Many people did. Electricity was the hot new technology of the time, and a lot of people played with it. He worked with some people to make a practical telegraph system, and part of Morse's contribution to that was developing the encoding of the messages. And he came up with a really elegant system. So each of the symbols in the language were represented by a series of dots, or a series of particles. Some of the particles were dots and some of them were dashes. And the difference was their length. So a dot was made up of a 1-bit and a dash was made up of 3 1-bits. And between the dots and dashes would be 0 bits. And depending on the number of 0 bits, that would determine if it was a particle space separating a dot from a dash, for example, or a letter space, or a word space. If you think about this in terms of music, a dot is an 1/8 note, and a dash is a dotted quarter note. So you just play those, and the zeros represent the rests. So a single 0 is an 1/8 rest, a dotted quarter rest would be 3 zeros, and a whole rest was actually 7 zeros, but that's close enough for jazz. It's also a time-based code. So Morse was concerned with wanting the most frequently used letters to transmit in less time than the least frequently used letters in order to reduce the total transmission time, which was very clever. And so 2 of the most popular letters in English are E and T, and each of those is spelled with a single particle. E is a single dot, T is a single dash. I and M are also very popular letters. I is 2 dots, and N is 2 dashes. So if you can remember the word time, you can remember the Morse code encoding for those 4 characters. Letter V, we can remember from Beethoven's 5th Symphony. 5 for V, dot, 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 dash. Okay, so everybody remembers the 5th Symphony, right? That's easy. The international distress signal is dot, 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 dash, 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 dot, dot, dot. It's sometimes called the SOS because the code for S is 3 dots and the code for O is 3 dashes. So if you can remember the SOS, you can remember the codes for O and S. Okay, everybody with me so far? We're going to remember H by thinking about the 4-H club. It's 4 dots for the 4-H club, and the head of the 4-H club, Harry Herbert Hoover Heaver. Then for the rest, I'm going to use a system of mnemonics. So I'll show you a letter and its code, and I'll give you a word in which all of the vowels in that word represent dots, and all the consonants represent dashes. And the word will also contain the letter. Okay, so the code word for A is am. Okay, everybody remember am? Okay, the code for B is bow. That's beautiful, my friend, is it not? B for bow. C is for code. So if you're trying to remember what's the code for C, it's code. Dash dot, dash dot. The code for D is D. Dee Snider, lead singer for Twisted Sister, he wrote the best protest song in the history of rock and roll. So remember, D is for D. That's pretty easy. E we already saw from time. E is the most popular letter, so E is for E. F is oofy. You just have to remember that. Seriously, oofy. And you need to remember this because someday you might be trapped in a mine or on a disabled submarine or in a spaceship and you have to communicate with the fleet somehow. You're going to have to know your Morse code. G is for GNU. That should be an easy one for programmers to remember. GNU is a source of a failed Unix clone and a free as in not free software license. H you'll remember from the 4H. It's 4 dots. I, you also saw from time, it's 2 dots, I. Hey, Jay, what do you say? I, JJJ. You what? I, JJJ. K is for kit. That's easy to remember, kit. And L is for aloe, soothing aloe. So don't forget to put aloe in your kit, Jay, okay? Aye, sir. We already saw M from time. It's good. Good. The letter M is good. N-O, no. Remember O from the SOS, it's 3 dashes. P. So next week, we're going to the P Expo, where they're going to announce a new mnemonic for remembering the letter P. Very excited about that. Q is a hard one. We can't spell many words out of Q, but Q words almost always have a U. So we'll have QU, and we'll want to put it in quotes. And we'll use the letter Q for the quotes, because quotes starts with Q. R is for R. That's going to be pretty easy to remember. S we already saw in the SOS. It's 3 dots. T we already saw with time. It's just a dash. U, out. O-U-T, out. Da-da-da-da. Right? The wise old owl. It goes hoot hoo hoo. I don't have one for X. We're at PayPal, so maybe Zoom wants to be that. I don't know. Just anyway. Y is for yuck. So I don't see any kids here, but if kids were here, I would expect them to remember Y is for yuck and F is for oofy. You'll probably remember more. And then finally, last of all is Z. What comes after zoo? Z-zoo, obviously. So you need to remember that because you could save the galaxy someday. So next we're going to look at another communication code. This was an updating of the Morse code called the Baudot code, which was invented by a Frenchman named Baudot, Émile Baudot, in 1870. So this was a 5-bit code. He's trying to make it easier to use the telegraph than Morse's system, which was a machine with one button on it, and you'd press that one button to make the code. Baudot had a keyboard that looked more like a musical keyboard. It had 5 keys, and you would play them as chords, and that would generate the 5-bit codes that would go down the wire. There was another inventor, Donald Murray, a New Zealander, who wanted to improve on the Baudot system. So what he did was he wanted to have it punch onto paper tape. So he had a normal keyboard looked very much like our modern keyboards, where you'd push a button and that would cause holes to get punched in a tape. And then after you punch the message, you then put that into a tape reader, which will then transmit the message. And on the other side, it'll get printed onto paper tape or maybe go to a printer. And so it would take a little bit longer to send the whole message, but it would use the communication channel much more efficiently. And in designing the code, he spread the letters around so that the most popular codes would have the fewest bits in them. Because the more bits that got transmitted, the harder the machinery would have to work, and the pins, the little knives, would wear out. And so he designed the code to try to prevent that. So for example, the most popular letters, E and T, each contain 1 bit. So they cause the least wear on the system. And some of the less popular characters like V has 4. So you don't use V as much because that would cause 4 of the pins to cut. And so being a 5-bit code, they could have at most actually 31 codes happening. But they came up with a way of almost doubling the size of the character set by introducing shift codes, the letter shift and the figure shift. When you go into figure shift, then the letters turned into other things like digits and special characters. And they used 2 shift codes because they were afraid if they had just 1 shift code, if the shift code got damaged in transmission, then everything was going to look stupid. The way it works now is if a shift code gets damaged, it only looks stupid until the next shift code. So eventually it'll recover. The next innovation was the Hollerith code. The Hollerith code was, Herman Hollerith developed a punch card system that was inspired by the Jacquard automated loom that put holes onto cards, and he developed machines that could put the holes on the cards and count the holes on the cards, and that was used in the 1890 census. The Constitution requires that we count each other every 10 years in order to figure out the composition of the House of Representatives, and the country got big enough that that got hard to do on pen and paper. So they commissioned Hollerith to figure out some machinery that could automate that, because it was going to, otherwise it was going to take a decade to make the count, and that wasn't going to work. And his system was very successful. Not only did they solve the problem for the census, but it created a new industry. And suddenly there were lots of companies that were making punch card equipment, and many of them merged together and eventually became international business machines. That company wanted to improve the amount of information that they could get into a card, so they re-architected it so that the card was laid out strictly in columns. Each column would represent 1 character. There were 12 rows, so it's basically a 12-bit character set to define the columns, except they couldn't make it a true 12-bit character set because the cards were very fragile. And if you punch out everything, then when the machinery read it, they'd have little wire brushes reading the pieces of paper, and if the pieces between 2 rows got too thin, it would damage the cards. And so they came up with a much more sparse encoding. So this is what they did. Each of the rows, if you give it a single punch, will represent a digit. And the top 2 rows will produce either a plus or an ampersand or a dash. And then they'll reuse the top 3 to make the letters. So if a 12 punch or an X punch, I'm sorry, a plus punch is punched out of the top, and a digit, then that forms the letters A through I. And if the minus sign is punched out and then a digit, you get K through R. And if the 0 is punched out and you have a 2 through 9, you get S through Z. And so there are 27 possible combinations that you could do that way, but only 26 letters, so they had to leave 1 out. And they left out 0, 1. Again, because if you had 0, 1 next to each other, the machines might rip that separator out of the card. And that piece of paper flying in the machinery could either cause the machine to jam or possibly to catch fire. So, you know, how many character sets do you know of that are designed intentionally to cause the equipment to not catch fire? So that was a concern in the design of this. They also needed special characters. And unfortunately, they didn't do a good job of specifying those. So every manufacturer, and in fact, different models of machines within the same manufacturer had different codes for the special characters. And so taking, say, a program from one machine to another was very, very difficult because there wasn't a standard encoding. Then computers start to happen. At the end of World War II, suddenly we start to see lots of computers, and most of the computers are being built with 6-bit character sets. 6 bits gets you 64 characters, ideally, and that seemed to be enough. So one of the first of those was something from IBM. They called it BCDIC, and this is the first version of it. And they just took their card reader that they were using for their punch card pre-computing stuff and just adapted it for this new stuff with the computers, trying to do as little rethinking as necessary. And so it's a bizarre looking code. First off, the printer that they were attaching their first computer to only printed 48 different characters. And so they didn't even fill up all of the 64. So there are lots of gaps in it. And there were characters that were used in the old punch card stuff, like the square lozenge. I don't know what that means. People used it because that was one of the only characters that were available, but I don't think anybody knew what it meant. And then they just took the encoding of the punch card codes and put them straight into the thing. So, you know, the 12 punch comes after the 11 punch and the 0 punch. It's just, you know, this is the laziest character set you can imagine. Unfortunately, it came from IBM, and so it was really influential. Meanwhile, there's another group at IBM that's trying to develop programming. There's a team that's developing a language called Fortran, which becomes the most important language in the world. And they specified a minimum character set that Fortran programs had to have, which the IBM machines didn't have. And so they tried to put the onus on the equipment part of IBM to add all of these characters to their equipment, because the characters that were in yellow here didn't exist yet. And this was actually kind of a brave thing for them to do, because if the manufacturers didn't go along with them, this was a dead language, because nobody could type it. And so they didn't ask for very much, right? You know, we really want a cross to do multiplication. We'll settle with the asterisk. It's already there. We're not trying to cause trouble. We're just trying to do the minimum. But we really do want an equal sign, and we've got to have a plus sign. Got to have a plus sign. So they didn't ask for very much. And eventually they got it. And it turns out all subsequent languages are based on the start that Fortran gave us. So IBM, in a later edition, had come up with some more characters and filled it out. It's still the same goofy thing, so it's a strictly compatible encoding. They added things like the cent sign, so they're being better for business. They added a bunch of weird characters. Here, like there's a delta and a radical. You know, who would ever use those? They actually they picked characters intending that nobody used them. The reason they did that was these characters were being used by their magnetic tape drive to as control characters to separate and block and stuff like that. And if you used those characters in your data and wrote them to tape, it would screw everything up because they would alias. So they picked codes that or characters that they hoped that people wouldn't use, and so it wouldn't cause the tape drives to fail. Then they started selling, IBM was an American company, even though their name was IBM, and they started selling stuff internationally, and they found, say, in Northern Europe, people didn't deal with 26 letters, they needed like 29 letters. So they indicated that those 3 letters could be substituted with local letters. This is where the I-18N problem starts. That, you know, we'll just take our stuff and start swapping stuff out, and that caused problems that went on for decades. We're just now getting to the end of that. There were other manufacturers who were doing their own stuff. So Control Data was a competitor of IBM. And you can see that they took the IBM character set and just tweaked it a little bit, added some things I liked, that they're more concerned with mathematics. So there's a not equal sign, and less than or equal, square brackets. We know how important those turn out to be. But they still kept the same stupid layout with the A coming after Z. Burroughs was another company that was building stuff. the Bros 5000 series of one of the smartest pieces of architecture that ever happened. And they improved it. So they got the A before Z now, so, but they're still broken up. So I plus 1 is not J. But they added the cross for multiplication, which is nice. And the thing I liked best about what they did was the code for 0 is 0. The code for 9 is 9. As a programmer, that makes so much sense to me. Of course 0 is 0. I mean, anything else would be stupid, right? That's just, what could be more natural? You know, this is God telling us this is what a character set is. Meanwhile, the US Army's Signal Corps, the Army is buying all these machines, and the Signal Corps has to figure out how to make them talk to each other, and they all have different character sets, and it's a problem. So they decide they're going to create America's character set, and all of these machines will have to learn to deal with that. So they come up with an 8-bit character set, and they put the interesting part in the upper end. I don't know why they did that, but they did. And they did some really nice things with that, like I plus 1 is J, and you know, it's continuous. That makes so much sense. And they left the other 64 characters unspecified. So what happened was there were 3 projects that were all going to use the new field data format, encoding. And they all thought that they needed additional characters. And there were that 64 characters that nobody was using, so they all started using that. And each of those projects had a different interpretation for what those characters should mean. And so when they tried to plug them all together, everything failed. So that was an early lesson that when you're designing computer standards, you have to be really specific. If you leave things underspecified, bad things can happen. And this is one of the early examples of that. Next step forward is ASCII. ASCII is developed by a committee made up of AT&T, which was the telephone and telegraph company at the time, and IBM and a bunch of other companies. And the intention was not to make a computer code, but to make a transition code that could be used by telegraphs and other communication equipment that computers could also use in signaling, but it wasn't expected that computers would use this as their internal character set. One of the really important questions they had to come up with a solution to was, how big is this character set going to be? Because the previous data communication standard was 5 bits, and they decided that wasn't enough because they wanted to be able to handle lowercase. So initially, they were going to make it 6 bits. And they were going to do the same shifting trick that Baudot did, except they would use it more like a typewriter. So there'd be shift uppercase and shift lowercase. And it would have been brilliant if they'd done this, because the way we would think about case today would be the same way we think about weight or decoration or slant, that it's just an extra thing that you could put on a letter. Uppercase and lowercase, they're just different glyphs for the same letter, same code. But they didn't do that, and as a result, they invented case tolerance and case intolerance. And the reason they did that was because they were afraid in transmission, the shift character might get garbled, and then things will look stupid. You know, the lowercase will turn out uppercase, and it'll look like someone is shouting in the telegram, and we don't want it to look like that. And so for that reason, they decided to double the size of the character set and turn it into a 7-bit character set. And we're still suffering for that. So this is how the set turned out. There are some things that are good about it and some that are bad. From the perspective of a data transmission format, it's reasonable that 0 is not 0. I would really like to have the zeros down there. And there's this large set of control characters. And you've probably seen these your whole career, you know, these weird little ACK. You know, what is ACK? I'm going to tell you what all of these mean, because you deserve to know. You've been kept in the dark for too long. So the first use of this code, like the later Baudot code, was going to be paper tape. And on paper tape, if no holes have been punched out of a row, then the code for that is 0. And all of the holes are punched out, the code is del. The idea was when you're typing a tape offline and you make a mistake, you go, oops, you back up the tape one row, press the delete key, and chunk, all of the knives come down and chop out all of the holes. And the receiver of the tape will recognize, oh, that's a place where a rub out. That's where the things have been, so I'll ignore that. So I have to ignore anything which is a 0, because that's just blank tape. And I have to ignore anything where everything's punched out. That is what those codes were for. There was a backspace code, which was Control H, and that meant move the print head back one character. It didn't mean erase the previous character. That's a user experience thing, and there was no user experience yet. There were no users yet. This was way before any of that. This was just move the print head. Later, these keys were both left on keyboards, and people tried to figure out, well, we should do something useful with them. And so we now have backspace, delete the previous character, and delete sometimes is delete the next character. That was never ASCII's intention. That's something that was discovered later. There were a couple of codes for operators to use. So if you were connected to some station and you don't know who you're talking to, you could send them the inquire code, and there would be a little drum on the teletype on the other end that would have a pre-recorded sequence of characters that would get sent back to you so you'd know who it is you're talking to. From a modern perspective, it's hard to imagine how could that happen? How could you be connected to a station and not know who you're connected to? And then trust them to tell you who they are. It doesn't make sense, but that's built into the code. And also, you can ring the bell on the other teletype. So you can go Control-G, ding, and over there, someplace else in the ether, a bell is going to sound. There are two characters for spacing. There is space, obviously, and tab. Tab was copied from typewriters. Old mechanical typewriters had a tabulate key, which when you pressed it would release the carriage so that it could move freely until it was obstructed by a mechanical tab stop. And ASCII anticipated that we might want to do that in the future, although it was already an obsolete idea, but they wanted to preserve that. But they didn't specify how to set a tab stop or even what the default tab spacing should be. So it's useless as a standard, but we still use it. And so whenever you have two things that people can choose, half of them will choose one and half will choose the other. So half of us are using space in our programs, half of us are using tabs, and we fight about it all the time. And there are problems in source control management and there's no value in it, right? It's a difference without any information because either one could work. And this goes on and on arguing about which one is better. And that question has no solution. If it did, we would have answered it by now, and we would have fixed it. So this continues to go on and on, causing countless dollars and pain and misery because we've been asking the wrong question. The question isn't which one is better. The question is which one can we get rid of? And it turns out the one we can get rid of is tab, because you can do everything you want with space. So the tab character is an anachronism that should have died with the typewriter. That is a fact. What's next? Format effectors. So they added some things for controlling the teletype. So on the teletype, there was a carriage return code, which would take the print element and move it back to the margin. And there was line feed, which would tell the platen to roll the paper up one line. And it was two separate codes. Today we think it should be just one code, but they had two. And partly they had two was that there were special tricks you could do, like maybe you could go back and strike something out. The other was that carriage return was slow compared to everything else, and so having a line feed happen after it gave the machinery a little bit more time to move the printhead over. So later we go to computerize the network, and the question is, well, which one should we use to do line end? Because that's what we care about, and there's no code for line end. There's just carriage return and line feed. And some people chose carriage return because, I don't know, just because they're two and half of them will pick one and the other half pick the other one. And then they go to a committee and try to decide who's wrong. And again, it's the argument, you know, who's right. And in the case of the internet, they came up with a mutually disagreeable compromise. They couldn't decide which one should we use, so they decided you have to use both. So if you look at the design of HTTP, which the whole web is built on, it says carriage return, then line feed, which is totally ridiculous because teletypes don't exist anymore. But it's in the internet standards. I don't know which one would have been the right answer, but clearly you have to use both is the wrong answer. Then in addition, there was form feed, which would tell the printer to kick out, to eject that page and to start the next page. And vertical tab, which was sort of like the horizontal tab, except it'd say go to some line. And again, it didn't give any way of understanding how to determine what that line was, so it's useless. So, you know, neither of these make sense anymore. They added some codes for device control. So these would control your paper tape punch and your paper tape reader on your teletype. You could turn it on and off remotely. They anticipated that someday there are going to be computer protocols, which was a good guess because, in fact, the future is protocols. And they made some guesses as to how that would work. So a message would start with a start of header code, and then there'd be a header which might address the message or something. Then start of text would indicate the beginning of the content of the message. And if it's a very long message, you could break it into blocks, indicating end of block. And at the end of the message, you'd say end of text. If a message was received correctly, then you would send back ACK. And if it was received incorrectly, it would send back NACK. And they intentionally tried to make them different by a number of bits so that the likelihood that an ACK would get garbled into a NACK was low. There was also synchronous idle. So there are two ways to think about how you transmit a character. There's the asynchronous format in which the line is empty, and then you send a start bit, and then a bunch of bits, and then an end bit, and then you're ready to look for the next start bit. Then there's what was called the synchronous mode, where you just send all of the bits all packed together. Then you have the problem of how do you know where a character starts and ends because you're just getting a bit stream. And so anytime the system was idle, you send the sync character. And the receiver will be looking for that pattern and will shift the bits until it sees that and goes, okay, we're locked now. And then it knows that all the characters that come after that will be on the correct boundaries. We don't do this stuff anymore, but it's still in ASCII. So a message might look like this. We'll say start of text, and then we'll have the body of the message and end of text. And we might optionally put a header on it. And if it's a long message, we can break it up. We don't do this anymore either. We've gotten much smarter about how to do protocols. Now, when you're all finished, you can send end of transmission, and that's supposed to hang up the phone, and we're gone now. But today, you know, it never ends, right? We're just, as long as we're connected, stuff's going on. And end of medium is something you might put on the end of a magnetic tape or something to indicate we've gotten to the end, there's no more. there are a couple of things which just indicate something really stupid happened. So substitute means we don't know what character was supposed to go here. So that's what this character is. And there's cancel. So you're sending a packet and you decide, yeah, no, we don't, never mind. So that cancels the never mind code. Again, in a modern network, you just would never do either of those. They anticipated that they might not have thought of everything, and maybe ASCII was too small, so they wanted some way to be able to grow it. And they provided a number of mechanisms for doing that. There was escape, which meant that the next character can have a different interpretation. One use of escape, and they were vague as to what that was. One use of it was take the next character, turn on the next bit. So you could get to an 8-bit character set by having double characters. Then data link escape was a similar idea. Sometimes it was also used to escape transmission codes. So if you want to include the, say, end of transmission character in your data, then you could put a DLE in front of it. And then they kept the 2 shift codes. They decided it wasn't safe to have the shift codes, but they put them into the character set anyway. So you could use them to shift into another character set, to shift out of ASCII and to shift back into ASCII. Then they added some characters for formatting data. So there's a file separator. A file is made up of groups. A group is made up of records. And a record is made up of units. And you've got all of these characters to separate them. Except it turns out that the fields in a record want to be labeled or named somehow, and sometimes a record wants to contain other records, subrecords. So they should have implemented JSON here, and they didn't, and it's really my fault, because I could have told them how to do this, but I was 6 at the time, and I had other things going on, so that didn't get into ASCII. So, yeah, so that's ASCII. That's how it turned out. So we look at ASCII today, most of those codes are problematic or obsolete, but we still have them. So this had a big influence on computer codes because everybody was wanting to connect to equipment that used these codes. And so if you adopted some form of these codes in your system, you could save a little bit of memory in translation. So there were a lot of systems who used what I called half ASCII. It's a 64-bit character set where you just take the ASCII code, subtract 32 from it, and you get a nice character code. And then Unicode happens. So Unicode starts off with some brilliant, brilliant people at companies like Xerox and Apple who are trying to make a system that they could ship to all countries and have the software work properly on all of them. And that was not possible in the ASCII scheme because every country would substitute some of the ASCII characters for its own, which meant that that data could no longer cross boundaries. So their goal was to have all of the characters of all of the living languages existing in 16 bits. And the thing that was hard about that was Chinese, Japanese, and Korean. That originally all 3 of those languages used the same character set, started with the Chinese model. But Japan and Korea, over many centuries, they started to drift. So they did something that they called Han unification, which was to try to reunify all of those character sets and reduce them into a single character set that worked for everybody. And in doing that, they could make it all fit in 16 bits, which was amazing. And they did it, and it worked, except it really pissed off the Japanese. They were really unhappy about that. So in the next version, they decided to change the goal. All of the characters of all languages, even dead languages, now expressed in 21 bits. was too late for JavaScript and Java. They were already committed to the 16-bit form, but modern Unicode got a million characters bigger. So it means it's going to be a lot more work now to finish Unicode, because it's not just finding everybody, all the characters that are being used. They have to find all the characters that have ever been used. And some of what they did, I really like, that hieroglyphics is now in the Unicode. Because I like hieroglyphics. And I like that I can and see that guy show up on my screen. That's really neat. But, you know, getting to the end becomes much harder. But for committees, that's great, because they're having so much fun, they really don't want to get to the end. They want something, and then in Unicode 6, we get emojis. That guarantees Unicode will never be finished. So Unicode contains, the first 128 characters of Unicode are the ASCII set. ASCII was never intended to be a character code, but it's now locked into Unicode, so it is a character code. And as you've seen, the first 32 characters are ridiculous, and they're there forever. I could imagine that someday Unicode gets replaced, but I can't see it happening in my lifetime. We're just stuck with it. It's the way it is. And there was this opportunity that was missed by the original ASCII standard. If they had stuck with the original 6-bit characters, so in the original 6-bit form, if you looked at the word sizes of computers, they were generally multiples of 6 because they wanted to be compatible with the character set. So I've worked with characters that were 12 bits, 18 bits, 24, 64, 48, and one of my favorite was 60. And it worked. But then ASCII kind of encouraged everybody to move up. So 7-bit ASCII caused the ascendance of computer architecture based on 8, 16, 32, and 64. That the influence of ASCII on IBSIDIC, and particularly on microprocessors. So the first microprocessor, the 8008, was commissioned by a company that built terminals. They went to Intel and said, we've got a design for a little CPU that we'd like you to make for us, and this is the architecture. And they wanted it because their terminals were getting so complicated that making them out of discrete circuitry was becoming cost prohibitive, and they wanted to replace it with a chip. The initial application for that processor was being a terminal, and terminals want to talk ASCII, so it wanted to be an 8-bit machine. Had ASCII not gone to 7 bits, it could have been a 6-bit machine or a 12-bit machine, and the future would have gone in a completely different direction. So if ASCII had been successfully completed as a 16-bit set, 36-bit architecture would have survived for a long time. And I think today we'd be looking at 72-bit architecture. The first microprocessors would have been 8-bit machine, or 12-bit machines, not 8-bit machines. Europe would have moved immediately to 12-bit character sets, just as Asia had to move to 16-bit character sets simply because it didn't fit. And by avoiding character substitution, most of the internationalization problems would have been avoided from the beginning. Ultimately, the world would have adopted an 18-bit character set. Unicode would have been an 18-bit character set that would easily have accomplished everything that we needed had ASCII done the 6-bit thing. And 72-bit CPUs would be standard today. So standards need to be reevaluated regularly and eventually replaced, as we discover that the assumptions made in the old standard, like a line hit could cause a shift character to get mangled, that's meaningless in our world today. The error correcting codes in our networks are so good we're completely unaware of them. The system just works. And to have that as a fundamental assumptions for what it means to be a letter, when do we stop and ask, did we get it right? But that's how progress works, that standards tend to accumulate crap over time, and in the end, you end up with that. Thank you.